Hello, welcome back. So we are going to continue chapter 3 about the mean, the average. Let me review briefly what we have done last time. So we defined the mean as the sum of probability weighted outcomes. That was the most important lesson we learned last time. And based on that definition, if you want to calculate the mean using a probability distribution table, what you have to do is to multiply the outcome to its probability. So multiply outcome probability and make another column that contains probability weighted outcomes. And then after calculating the probability weighted outcomes, sum all of them to get the mean. That's how you calculate the mean, right? And then as an example, we considered car sales uh, dealers performance evaluation, and at the end of the last uh, lecture, we learned an interesting and possibly useful, very useful uh, result, saying that suppose that you have an original random variable x. You know the distribution of x and the mean of x, but you are interested in another or different random variable y. So you transform x into y. For example, in our previous example, we changed number of cars into net profit, or you may think about the transformation between like different currencies, or inches to meters, or like Fahrenheit to Celsius. So there are a lot of transformations that satisfy this relationship. It's a linear relationship because the new random variable y is made of x times something plus something, right? So multiply something and add or subtract something. That's a linear relationship. So if the new variable is a linear transformation of the original random variable, then the new variable's average, the new variable's expectation also satisfies the same linear relationship with the original variable's expectation. That's this is what we learned, and it is very useful because, so think about this. Suppose that you know the so if you are interested only in the mean of the new random variable, what you need is the linear relationship, which is usually obvious, and also you only need the mean of the original variable. You do not need to know how the probability is distributed. You just need the mean, right? So it simplifies a lot of work. However, what's important here is it has to be linear. The relationship must be linear. So let me think about another example, similar example, but just to practice the transformation. So I introduced, by the way, there was a student who kindly sent me an email uh, after watching one of the earlier videos, and in which I mentioned my son. My son went to kindergarten, so so today was his fourth kindergarten day, and he's doing well. So so imagine you have a son, 5 years old, going to kindergarten. He does not know what is the Disney World yet because of the COVID. Uh, Fortunately, we could go to the Legoland, recently opened in New York State. Um, but these maybe someday we are going to uh, go to the Disneyland. I'm very looking forward to that trip. So suppose that how many times can I go to Disney World next year? Let's just think about this. in terms of probability. So I think so it's a kind of realistic, very realistic distribution. I think 50% of the possibility is that I will not go to Disneyland, Disney World, and 40% chance is that our family may go to Disney World next year. And finally, if I'm extremely lucky or some luck happens, I may go twice. If my son wants to go there too much, then I may go there twice. So we have I have this kind of probability distribution of the number of trips next year to Disney World. Then based on this distribution table, let x be the number of trips. Uh, can you calculate the expected value of the random variable? That is the expected number of trips to Disney World. Try this as an exercise and pause the video, do the exercise, and um, and then resume. Okay, I will show you the answer in 3, 2, 3. The answer is the answer is zero point 0.6. That's easy. Just multiply outcome to probability, outcome to probability, outcome to probability. Then you get these numbers. Their sum is the expected value. So I expect our family will be going to uh, Disney World zero point 0.6 times. So of course, zero point 0.6 times it's just mathematical number, um, and like less than once next year. That's my expectation. Okay, then what I'm more interested in is the cost of a trip. So suppose that for simplicity, I assume that if I go to Disney World, it costs me $1,000. See, uh, and I would like to think about the budget. So I will define a new random variable y as the total spending on the trip, like all the trips to Disney World. So that is it is it's clear. So if I do not go to Disney World, the spending will be zero. If I go twice, $2,000, right? Then can you calculate the expected spending next year on Disney World? Try this, and I'll show you the answer. 1, 2, 3. So what you have to do is pretty simple, actually. There are two different ways. One way is to use the already calculated mean for the original random variable and the linear relationship with the new random variable. That's the first method. And the second method is rewrite a table, remake the probability distribution table for y. So do the transformation by hand. So let me show you the first one. So the first one, we know that the spending y equals 1000 times x. Simple, right? For each trip, I spend $1,000. So y will be 1000 times x. And we already know that expected value of x equals 0.6. So average number of trips is 0.6. Therefore, we know that those two have linear relationship, and I know the original mean. Therefore, the mean of the new random variable is just plug in the mean of x in this linear relationship, which is $600. Simple, right? So if I trip once, I'll spend $1,000, but I expect to travel 0.6 times. Then the expected spending would be 0.6 of 1,000. So this is the simpler way, but more complicated way is like this. First, make another column which contains the value of y. So I transform the number of trips into dollars. How many dollars I spend. So it's either 0, 1,000 or 2,000. Simple. Probabilities are still the same because x equals to 1 is the same event as y equals to 1,000. So x and y have just different numbers of zeros. Otherwise, everything is the same. So probability do not change. Then we are looking for the mean of y. So now what we have to do here is multiply the outcome for y to the probability. So 1,000 times 0.4, 2,000 times 0.1. Then the weighted outcome, now in terms of y, in terms of dollars, is 0, 400, 200. And if you sum these three numbers, you get $600, which is the same result as before. So these two methods, I just showed you two different methods. Both are correct. In this case, both are correct, but the difference is the earlier one, the former is the simpler one. But it's a little bit risky because if you are not sure if the relationship is linear, in this case obvious, but if it was not linear, then this result does not hold. However, this method holds all the time. No matter what the transformation looks like, this is true. This is more fundamental way, more like the basic way to calculate the mean. Therefore, if you are not sure what is linear relationship, then try this. That's what I like to say. Okay, let me change the example a little bit to make it a little more realistic and a little bit make the problem a little more complicated and tricky. So think about this. You found a discount ticket admission. So if you like it's on eBay and you have to buy it now. But I'm thinking about so this ticket can be used next year, but I have to decide it right now. So the deal is I can buy the ticket at for $700 instead of 1,000. So instead of 1,000, it saves if I take the ticket. I can spend the spending reduced to $700. But if I have to pay $700 now, even if I do not use it later, because I don't know what happens next year. So then think about this. So I will define another random variable z, which is defined as the total spending if I buy this discounted ticket. If I take this deal, buy the ticket on eBay right now, without knowing what would happen next year, then in this scenario, it's right. So this is very likely scenario. Um, and then my spending z is a function of the number of trips. So x, I don't know what happens to x, and depending on x, z will be also determined. So z, the total spending if I take this ticket, will be like this. If I do not go to Disney World next year, still I have to pay $700 because I paid it now. I just paid it now. I assume that there is no resale, so I paid $700 now. So I paid. That's my spending. If I go once, then still I pay $700 because I can use the discount ticket. But if I go twice, then I have to buy another ticket, an additional ticket, at the regular price of $1,000, right? So in this case, the transform it's another kind of transformation, but it's a little bit different. So we defined a new random variable, and of course the probability distribution the same. Then can you calculate the mean of z? So try this. I will stop the video here, and after doing the work, go to the next video. See you there. Bye.